Welcome to the third lesson in Module 7. We're sticking with our theme of impacts on biophysical systems by taking a look at climate change impacts in water. After this lesson, we move on to climate change impacts on humans, including the implications for cities and for developing countries. As always, this is just an introduction to high-level ideas, so I encourage you to take a look at the work of the Intergovernmental Panel on Climate Change Working Group 2, which focuses on adaptation and impacts. If you live near an ocean or depend on it for your livelihood, give some thought to changes that you may have already seen. This might be good fodder for assignments 1 and 2 in this course, but is also just an important part of connecting the global trends in climate change to the way we actually live in local spaces. In this lecture, we're going to start out by remembering the importance of oceans as moderators of global climate, but also the many pressures we're putting on them through our activities, not just climate change. Then we'll think about the impacts that scientists have observed in our oceans, including increasing temperatures, ocean acidification, and ecosystem degradation. Finally, as you've already learned, many systems don't operate in linear terms, getting predictably and incrementally better or worse. Thresholds and feedbacks are important characteristics of systems like the ocean, and some scientists are exploring whether the state of our oceans is facing a tipping point. You've already learned in earlier parts of this course that oceans are fundamental elements of the climate system. They modulate the global environment by regulating the climate through biogeochemical cycling. Of course, they're also home to complex ecosystems and thousands of species, many of which are of crucial economic and social importance to humans. 40% of the world's population actually lives near an ocean, making the oceans the building blocks of our economies and our societies. Much like the coastal systems that we explored in Lesson 7.2, oceans suffer from a number of coinciding impacts. In addition to rising global temperatures and increasing acidity, we're also putting pressure on our oceans through overfishing, through pollution, and the introduction of non-native species that alter the delicate balance of ecosystems. As global temperatures rise, so do the temperatures of the oceans. This graph shows the very strong trend in increasing ocean heat content observed since 1955. The change isn't consistent, of course. Seasons, ocean currents, and natural variability all affect the temperatures we find in various places and from year to year. Corals are some of the first creatures to suffer from this rise in temperature. Coral bleaching happens when temperatures rise about 1 degree Celsius higher than normal for a period of around 4 weeks. When it gets too hot, corals actually kick out tiny creatures that they normally live in symbiosis with, turning white and really fragile in the process. In the Western Pacific Ocean, one of the largest bleaching events occurred in 1998, during which scientists estimate 16% of the world's corals died in a single event. What remains after the bleaching usually houses a different mix of species and is less structurally complex. This is one area, though, where it's tough to disentangle the effects of climate change from other processes at work in the ocean. Ocean temperatures naturally shift, along with the Pacific Decadal Oscillation and the El Niño Southern Oscillation. Overfishing and pollution also directly affect the health of corals. As we'll see, the concentration of CO2 in the atmosphere also affects ocean ecosystems, so this is a pretty complex picture. When we think about the impacts of our combustion of fossil fuels, we most often think about the greenhouse gases that are released and the effect they have in the atmosphere, or the greenhouse effect. There's another way, though, that carbon dioxide affects the planet. As you know, concentrations of carbon dioxide in the air are much higher now than they were before the Industrial Revolution. Rather than just hanging out in the atmosphere, much of this carbon dioxide actually finds a new home, the oceans. CO2 dissolves into the water in our oceans, reacting with water to form carbonic acid, or H2CO3. Through another series of chemical reactions, hydrogen ions and bicarbonate ions are produced. This is important because the higher the concentration of hydrogen ions in the ocean, the lower, or more acidic, the ocean is. This has important implications for many of the creatures that live in the ocean. In particular, some plankton, corals, and mollusks that build their shells out of calcium carbonate have a difficult time getting the carbonate they need. These organisms form the foundation of food chains in the ocean and also join together to create habitats for other animals in the form of coral reefs. Scientists estimate that the concentration of hydrogen ions in the ocean has gone up by around 30% since the Industrial Revolution, and anticipate significant effects on ocean ecosystems. There's not enough data here though, so some of these findings are just emerging. Oceans don't just suck up carbon and moderate temperature fluctuations. They also act like huge conveyor belts, moving heat around the globe. Oceans actually move the same amount of heat around the planet as the atmosphere does. It's this conveyor belt that makes Canadians jealous of the relatively mild temperatures in Northern Europe, despite rough similarities in latitude. This conveyor belt, or thermohaline circulation, is pushed along in part by the differences in density between salty ocean water and fresh water from ice and rivers. If too much fresh water enters the system from melting ice, the conveyor belt can slow down over time. Ocean circulation is also driven by flows of heat through convection. Models have shown that this is actually a very fast process, and the warming associated with a quadrupling of CO2 in the atmosphere may be enough to cause a rapid shutdown of the Atlantic Ocean circulation that makes it so balmy in Europe. The important lesson here is that ocean circulations are nonlinear. The science suggests that abrupt changes and thresholds in the system are possible outcomes of a warming climate. As with species on land, some fish adapt to changing conditions by finding new places to live that are more comfortable. Temperatures in the ocean don't rise uniformly, but rather in pockets. So scientists are observing changes to the range of fish species, many of which form the foundation of our fisheries. As freshwater ice melts and flows into the ocean, the salinity levels of the ocean changes. This has caused plankton, or tiny organisms that are a major food source for larger species, to move out of their traditional territory. We're also seeing diseases and non-native species in places we haven't seen them before. These changes are occurring around the globe, from the North Atlantic to the Southern Ocean, and from the Mediterranean to the Bering Sea. Of course, it's not just the ocean that matters. Some fish in North American lakes and rivers are migrating anywhere from 6 days to 6 weeks earlier than they once did. In East Africa and in Europe, scientists have noticed a decrease in the numbers of diatoms, a form of algae that's the foundation of food chains. We've learned that oceans are highly non-linear systems. We have many impacts occurring simultaneously, from higher temperatures to higher acidity, and we may be reaching a tipping point. To learn more about this tipping point, check out this video from PBS. While you're watching, keep in mind the complicated question of acting in the face of uncertainty. Do we know enough to change behaviors and policies to respond to the potential of a very different future for our oceans? In this lesson, we've surveyed some of the key impacts of climate change and the emission of greenhouse gases on the planet's ocean. This is a complicated picture. Multiple stressors interact to create the picture we see today. Corals, fish species, and even ocean circulation patterns are being affected by both rising temperatures and the higher concentrations of CO2 in the atmosphere. Some scientists think that this is bringing us to the precipice of a tipping point, after which our oceans may function very differently from today. So what does this all mean for us? As we continue through this module, let's move on to the impacts of climate change on humans, especially those in cities and in developing countries.